Hi, welcome to breadth first search traversal algorithm for finding shortest path connectivity for given graph. Here we are having two different graphs. One is a directed graph, it is called digraph, and another one is undirected graph. So undirected graph is having bidirectional edges, directed graph is having unidirectional edges. So now the breadth first search can be implemented to directed graph and undirected graph, and also weighted graph, unweighted graph. Here the breadth first search will visit all the vertices available in the graph systematically. So how it will work? So before starting to breadth first search, we should check either the given graph is undirected graph or directed graph, right? Weighted graph or unweighted graph. So if it is undirected graph, you can select any vertex as a source, and from that source you can visit all the vertices available in the given graph through any other vertex. Suppose if I want to visit the 3, you can go through 2, or you can go through 1 5 4 3, like that. So any way you can select based upon the procedure. But when you are taking the directed graph, if the directed graph, when you are selecting the source vertex, then you have to see that should have path to all the vertices through other vertex. Suppose if you select the G, it is having the path to D, from the D to F to C it is having, and from the D to E it is having, and like that it is having the path from G to H, H to B, and H to A. But when you are selecting the vertex A, here the if you select the vertex A, it is having the adjacent vertex B. After that there is no path, so you cannot visit all other vertices from the source. So what we have to do, whenever we are selecting the source vertex in the directed graph, we should check is there any path available in the from the source to other vertices, because that should have connectivity, right? So after that we can get the input data for the graph using adjacency matrix or adjacency list. So adjacency list or adjacent matrix will have the adjacent nodes for each and every vertex available in the given graph. For example, for E, adjacent vertices are here only the G. Okay, so like that for D, the adjacent vertices are E, F, and C. So E is on adjacent vertex, F and C. So we have to use either adjacency matrix or adjacency list to get the adjacency nodes of given graph for any vertex. Then we can use the Q data structure to fill the input data based upon the procedure, right? So from the Q, you can select any vertex as a source vertex, that is the root vertex of the given graph, not given graph, going to find the shortest path. So that will be selected from front node of the queue. So whenever you are having the queue, the node will be accessed by using the peak, okay, peak pointer that will be available at the front of the queue, right? We will insert the new data in the rear side of the queue. So based upon that queue data structure, we are selecting the node which is available in the front pointer accessed by peak pointer. Okay, then we can dequeue, that means remove that selected vertex from the queue, right? That is the initial element. Then enqueue all the adjacent vertex of deleted element from left to right. That means suppose if your source vertex is D, if your source vertex is D, then D is inserted enqueue into the queue, then it will be removed. Then adjacent vertices are E, F, C. So you have to enqueue that E, F, C into the queue. So that's what it says, enqueue all the adjacent vertices into the queue from left to right. Then if a selected vertex does not contain adjacent vertices that are need to be investigated, then simply dequeue from the front pointer and resume the operation. That means, suppose if you select B, if it is B, for B it is not having any adjacent vertices. So what we can do, simply we can DQ and proceeds the next process. That's what it says. So if adjacent vertex emerges that has been previously investigated, that means D is already investigated here. Still, if you have if you have path, suppose if you are having the path from C to D, then when you are DQ the C, you will get the D, right? But D is already visited. That means previously it was investigated, so need not to add into the queue, no need to add into the queue, so we can skip that. If it is already visited or connected, so need not to be enqueue into the queue. So we have to repeat this until the queue becomes empty, right? And also the all the nodes has to be visited by connecting the path, right? So this is the way to use breadth first search algorithm to find out the shortest path. The pseudocode is given here. The number of vertices are passing. Initially, if v equal to null, that means number of nodes equal to null means just return the given graph is empty. Then otherwise, if it is having number of nodes, for example 2 or 5, you can enqueue the vertex v. Then if q is not empty, then you have to select that particular node from the front pointer. Then you have to delete that. So after deleting, we have to check that node is visited or not. If it is not visited, you have to mark that as a visit. And then you have to identify the adjacent vertices to the v. So if it is e means, so E is deleted in this location, E is marked as a visited. Then for the E, adjacent vertices are here G. So G is the adjacent vertices that has to be checked. Is it visited or not? It is not visited, and also it is not queued. So we are going to enqueue into the given queue. So we have to repeat this until queue is not empty. Still G is not empty. So we have to dequeue that G. Then G is checking it is not visited. Yes, it is not visited. Then G will be added as a visited. Then if it is visited, then we have to take that G to identify the adjacent vertices of G. For adjacent vertices of G, we are having H and D. So now we are going to add that D and H here. Any order you can form. Either you can add H and or D, or D or H. Okay, first or second. So now it is added into the queue. Again, it is going back, checking the queue is not empty. Yes, it is not empty. So then you have to take the D. So like that, you have to keep on do it until the number of vertices are visited. So that can be followed by using the queue. Once queue becomes empty, you can stop the algorithm. So this is the way to use the breadth first search for finding the shortest path. Thanks for watching.